So first I'll construct a general velocity triangle. So the velocity triangle, as we had discussed in theory class, it can be constructed in two different ways. One is with common base and the other one is with common apex. So we'll start with the most preferred one is common base for axial flow as well as tangential flow turbines. If it is a reaction turbine, we cannot use, or if it is a radial flow turbine, we cannot use common base because the base values will be different. Here in this case, the base is the tangential speed of the blade, that is u. So here I have drawn a velocity triangle. Now I will name the parts. So the base from here till here, it is u. That is the tangential speed of the rotor or the runner. And then we have velocity v1 here. This is velocity v1, and this is, since u and v1, u is the tangential speed of the blade, that is the blade is moving and the fluid is also moving. So because of that we will have relative velocity, which we call it as vr1. And since we are dealing with vector here, by the magnitude alone, the direction of the vector also matters. So the angle made between v1 and u, I'll call it as alpha 1, and the angle made between v2 and vr1, I'll call it as beta 1. Now, this absolute velocity v1 can be resolved into two components. One is horizontal component and the other one is the vertical component. If you remember, when you are dealing with forces, you try to resolve the force into vertical and horizontal component to add up to find out the net force. Generally what we do is we will convert, or we will resolve all the different forces acting on an object into vertical and horizontal components, and then we add all the horizontal components and then we add all the vertical components, and after that we will find out the resultant force. Similarly, since force is a vector and velocity is also a vector, so what we have to do is we need to resolve that into vertical component and horizontal component. The horizontal component here, we call it as the tangential velocity component or tangential component of absolute velocity, which is vu1. And the vertical component, we call it as the flow velocity vf1. So we have two components for v1. So this portion of the triangle, it's a right angle, it will always be a right angle triangle, and that is present only uh, that is present only because we are resolving v1 into vertical and horizontal component. Okay, that is one triangle which is present here, and the other triangle is the triangle formed due to u, v1 and vr1. These are the two triangles which are present at the inlet. So here the term, the subscript 1 represents inlet. So 1 is always inlet and 2 is outlet. So we need to remember this: wherever it is 1, it is inlet, and wherever it is 2, it is outlet. So now let's come to the outlet velocity triangle. So we fill in the shape triangle. So from same end, v2 will start. So this line, which is cutting one end of u, that we call it as v2. And wherever we have vr1, the origin of vr1, at the same place we'll have the origin of vr2 in common base representation. So now we have v2 and vr2. The angle made by v2 with respect to u, I'll call it as alpha 2, and the angle made by vr2 with respect to u is beta 2. Beta 1 and beta 2 are the angles of the blade, and alpha 2 are the angles of the rotor. So first I'll construct a general velocity triangle. So the velocity triangle, as we had discussed in theory class, it can be constructed in two different ways. One is with common base and the other one is with common apex. So we'll start with the most preferred one is common base for axial flow as well as tangential flow turbines. If it is a reaction turbine, we cannot use, or if it is a radial flow turbine, we cannot use common base because the base values will be different. Here in this case, the base is the tangential speed of the blade, that is u. So here I have drawn a velocity triangle. Now I will name the parts. So the base from here till here, it is u. That is the tangential speed of the rotor or the runner. And then we have velocity v1 here. This is velocity v1, and this is, since u and v1, u is the tangential speed of the blade, that is the blade is moving and the fluid is also moving. So because of that, we will have relative velocity, which we call it as vr1. And since we are dealing with vector here, by the magnitude alone, the direction of the vector also matters. So the angle made between v1 and u, I call it as alpha 1, and the angle made between v r1 and direction of u, I call it as beta 1. Now, this absolute velocity v1 can be resolved into two components. One is horizontal component and the other one is the vertical component. If you remember, when you are dealing with forces, you try to resolve the force into vertical and horizontal component to add up to find out the net force. Generally, what we do is we will convert, or we will resolve all the different forces acting on an object into vertical and horizontal components, and then we add all the horizontal components and then we add all the vertical components, and after that we will find out the resultant force. Similarly, since force is a vector and velocity is also a vector, so what we have to do is we need to resolve that into vertical component and horizontal component. The horizontal component here, we call it as the tangential velocity component or tangential component of absolute velocity, which is vu1. And the vertical component, we call it as the flow velocity vf1. So we have two components for v1. So this portion of the triangle, it's a right angle, it will always be a right angle triangle, and that is present only uh, that is present only because we are resolving v1 into vertical and horizontal component. Okay, that is one triangle which is present here, and the other triangle is the triangle formed due to u v1 and vr1. These are the two triangles which are present at the inlet. So here the term, the subscript 1 represents inlet. So 1 is always inlet and 2 is outlet. So you need to remember this: wherever it is 1, it is inlet, and wherever it is 2, it is outlet. So now let's come to the output velocity triangle. So v1 is nil in the value from same end, v2 will start. So this line which is cutting one end of u, that we call it as v2. And wherever we have vr1, the origin of vr1, at the same place we'll have the origin of vr2 in common base representation. So now we have v2 and vr2. The angle made by v2 with respect to u, I'll call it as alpha 2, and the angle made by vr2 with respect to u is beta 2. Beta 1 and beta 2 are the angles of the blade, and alpha 2 are the angles of the rotor. Okay, now we have v2. v1 na hege we had resolved it into horizontal and vertical component. V2 can also be resolved into vertical and horizontal component. The vertical component of V2 we call it as VF2, and the horizontal component of V2, which is from here, from this point till here, that we call it as VU2, the tangential component of absolute velocity at outlet. That is VU2. Now, remember the Euler's energy equation. The energy equation was equal to U1 VU1 plus or minus U2 VU2. So here we have plus or minus. So this depends on the direction of VU1 and VU2 with respect to U1 and U2. So here we are dealing with axial flow turbines, so we don't have U1 and U2. So I can rearrange this as U into VU1 plus or minus VU2. Okay, U into plus or minus VU2 is the equation for energy transfer in the case of an axial flow turbine or a tangential flow turbine. But here, uh, the plus or minus, this sign depends on the direction of VU1 and VU2 with respect to U. So U the direction ಮೇಲೆ VU1 and VU2 depend ಆಗಿರುತ್ತೆ. Now the direction of VU1. So if you look at the V1, V1 is towards right and it's moving towards right and upward direction. So horizontal component will be towards right. Direction of V1 is towards right. Now look at V2. V2 is moving towards left and towards upward. So the direction of horizontal component of VU2 will be towards left. Now both are in opposite direction. So in vectors, both are in opposite direction. Then we have to add. So the total difference between VU1 and VU2 will be, I'll call it as delta VU, and that is this entire length. This is applicable only when VU2 is in opposite direction of VU1. So in that case, energy equation can be written as U into VU1 plus VU2. If both are in the same direction, then we have to write energy will be equal to U into VU1 minus VU2. So instead of writing VU1 plus VU2 or VU1 minus VU2, what we do is we write energy equation as E equals U into delta VU, where delta VU is the horizontal distance between VF1 and VF2. You will construct velocity triangles for different cases. This is a general velocity triangle. This is not applicable for every case. So when you write velocity triangle for different case, you will see that the difference of VU1 and VU2, that is this value, we will get it as the horizontal distance between VF1 and VF2. And while solving the problems, you can use two different methods in solving turbo machine problems. One is analytical method. And the other one is graphical. So in analytical method, we use the trigonometric relations that are for beta 1, maybe cos beta 1, sin beta 1, tan beta 1, and the Pythagoras theorem, because we're dealing with some right angle triangles here, then cosine rule. So using these kind of relationships, we will find out the different velocities, and then we'll find out the energy output, that is work done or change in enthalpy, it is also equal to change in enthalpy of delta H naught. So change in enthalpy and then the efficiencies which we discussed in theory classes. So we'll calculate all those things with the help of different velocities here. Okay, so we can find these what is velocities analytically, or we can construct the velocity triangle by taking a suitable scale. If V1 is 100 meter per second, then what we do is we take a scale of maybe 1 is to 10 meters. We'll write this for will represent V1 as a line with 10 centimeter as length and alpha 1 as its direction with respect to u. Like that, by taking suitable scale, we can construct the actual velocity triangles, and then from there you can directly measure what is the length of VR1 and multiply that with the scale factor, and you will get the velocity. From that you can find out again the energy or the enthalpy or the different efficiencies required for us. So this is the basic of solving problems in turbo machines. First we will solve problems with analytical method. After a few days we will solve problems about the data. The given data here are, we have two data here. One is absolute velocity at inlet. That is V1. V1 is 10 meter per second and it is in axial direction. Then we have the rotational speed, that is u. U will be equal to, or you can call it as u1 because we don't know whether it's an axial flow uh, turbine. So u will remain same at inlet as well as at outlet, and that is 20 meter per second. Now we need to find out the magnitude of relative velocity, that is VR1 will be. So we need to find out these values. It's a very simple problem. So in this problem, I'll write the velocity triangle here. As I said, there are two types of data in velocities. One is related to fluid and the other one is related to the rotor. Okay, the absolute velocity or the tangential velocity or the flow velocity. These three velocities are related to the fluid and u, that is the rotational speed in terms of RPM or in terms of meter per second, it will be given. So that will be related to the runner. So you need to be very careful. And as I said, beta 1 and beta 2 are the angles of the blade, that is the moving blade, and alpha 1 and alpha 2 are the angles of the fluid at the inlet and outlet. So those two are fluid angles or the nozzle angles, and beta 1 and beta 2 are the moving blade angles. So in some cases they will tell you only the fluid other. They will give you data as blade angle. So if they have given any data as blade angle at inlet or outlet, then that should be beta 1 and 2. If they say the fluid is entering at an angle of 25 degree or 30 degree, then that should be the fluid angle, that is V1, angle of V1 as well as angle of V2. So if the data angle is given with respect to the fluid entry and exit, then it is alpha. If it is given with respect to the blade, in the data, if they specify it as blade angle of the blade, then it is beta 1 and 2. At inlet it is 1 and at outlet it is 2. Now let us try to construct the velocity triangle for this case. We have u, sorry, we have u. So I have written the horizontal line, that is u, and then we have v1, and the angle of v1 is 90 degree here because the v1 is axial in direction. So the angle will be 90 degree between u and v1. So alpha 1 will be equal to 90 degree because v1 is axial. Okay, so here this is u and this is V1. Now, if you join the two free ends of V1 and U, you will get VR1. So for a vector, so this portion, so I'll write a vector here. So we have a vector here with a arrow mark. So uh, the portion towards the arrow mark, we call it as head, and the portion which is away from the arrow mark, we call it as tail of the vector. So if you join the head of U and head of V1, then you will get VR1. So I'll do that now. I'll join from here till here. Now what we have, this line, this is our VR1. We need to find out the magnitude of this as well as the angle alpha, sorry, the angle is beta 1. We need to find out the angle beta 1 and the magnitude of VR1. This is a pretty straightforward problem where you can use Pythagoras theorem to find out the value of VR1. So I can write VR1 will be equal to square root of V1 square plus U square. And you can substitute the values and you can tell me the value of VR1. Try to find out. So V1 is 10 squared plus U is 20 squared.
सर ನೀವು ಸ್ಕ್ರೀನ್ ಶೇರ್ ಆಗಿದೆ 22.36
ಎಷ್ಟು
22.36
It is 22.36 meter per second. So that is the magnitude of VR1. But since VR1 is a vector, we need to also find out the direction or the angle. So to find out that, I can use here, I know V1 and I know U. So I can use tan beta 1. So tan beta 1 will be equal to V1 divided by U. Or in other terms, I can write beta 1 will be equal to tan inverse of U1, sorry, V1 by U. So if I substitute the values here, it is tan inverse of V1 is again 10 divided by U is 20. What is tan inverse of 10 by 20 or half?
26.56
Beta 1 will be equal to 26.56 degree. So that is the direction of the relative velocity, and the magnitude of relative velocity is 22.36 meter per second. This is a very simple problem. You will not encounter these kind of problems in, yeah. Here, is the problem visible properly? We have a fluid. Fluid flows through one stage of a turbo machine. The velocity diagram is as shown in figure A. So this is figure A. First we need to find out, is this a power generating or power absorbing turbo machine? So we need to find out, is this a power generating or power absorbing turbo machine, and that depends on the value of energy transfer. If the energy transfer is positive, then it is a power producing turbo machine or power generating turbo machine. If it is negative, then it is a power absorbing turbo machine. Then we need to find what is the change in the total enthalpy. So as I said, total enthalpy is nothing but the energy transfer. So we need to find out energy transfer here, and then we need to find out the utilization factor. Okay, these are the things which we need to find out with the given velocity triangle here. The velocity triangle is given, so we need to refer that and we need to find out the required parameters. So first, let us try to find out different velocities here. So Vf value is given as 200 meter per second, and all the angles are given. First, let me label all the angles. So here we have this is the direction of u. So u is towards right. So angle made by u and v1, we call that angle is, sorry, alpha 1, and I'll highlight the inlet velocity triangle here. So from here, so I'm drawing a line for inlet velocity triangle here. From here till here it is u, and this is vr1. So for the inlet velocity triangle, this is v1 and this is u. So this is alpha 1, and here we have vr1 and this is u. So this angle is beta 1. And now I'll highlight the outlet velocity, and then we have Vf here. So this V1 is resolved into horizontal component, that is Vu1 here, and vertical component Vf. So Vf is same for both inlet and outlet velocity triangle. Now I'll highlight the outlet velocity triangle. So for the outlet velocity triangle, we have V2 here, and then from here till the end it is U. And if you join V2 and U together, then we'll get VR2. That is the outlet velocity triangle. And here the angles V2, the angle made between V2 and U is alpha 2, and the angle made between VR2 and U is beta 2. So these are the angles. First, let us list out all the data. So data in this problem are uh, Vf is given as 200 meter per second. Then alpha 1 is given as 45 degree. Beta 1, beta 1 is given as 60 degree. Alpha 2 is given as 60 degree, and beta 2 is given as 45 degree. These are the data given here. Now we need to find out VU1 and VU2. Once we know those two values, then we will be able to find out energy transfer. And from the energy transfer, we can say whether it's a power generating or power absorbing turbo machine. Now let us start with VU1. So VU1, we need to find out VU1. VU1 is the horizontal component here, that is from A to C in the velocity triangle. So I know OC, I need to find out AC, and I know the angle, I know this angle which is making the right angle triangle, that is alpha 1 is 45 degree. So if I take cos alpha 1, cos of alpha 1, then that will be equal to, I'll take tan alpha 1 here. If I take tan of alpha 1, so that will be equal to Vf divided by opposite divided by adjacent, that is Vu1. So Vu1 will be equal to Vf divided by tan alpha 1, or 200 divided by tan 45. So what is tan 45? Tan 45 is 1. So Vu1 will be equal to 200 meter per second. Now Let us find out V1. So to find out V1, V1 is hypotenuse and VF is the opposite side. So I'll take sine alpha 1. So that will be equal to opposite divided by hypotenuse, that is VF divided by V1, which implies that V1 will be equal to VF divided by sine alpha 1. So that will be equal to 200 divided by sine 45. So what is 200 by sine 45? V1 will be equal to V1 will be equal to 282.8,
0.84.
okay, 84 meter per second. Now let us find out V2. So for V2, I know VF and I know the angle alpha 2. So I'll take sine of alpha 2 and that will be equal to VF divided by V2, which implies V2 will be equal to VF divided by sine alpha 2, which is 200 divided by sine 60. So V2 will be equal to, it is 230.9 meter per second. I request everyone to use your calculators and calculate these values. Now we need to find out VU2. So VU2, if I take this right angle triangle, then VU2 is adjacent side and VF is opposite side. So I'll take tan of alpha 2. So that will be equal to VF divided by VU2. So VU2 will be equal to VF, that is 200 divided by tan alpha 2 is 60. So VU2 will be equal to
115.47.
115.47 meter per second. Now we have calculated VU1 and VU2, and now we need to calculate U. So to calculate U is from A to D for the inlet velocity triangle or from B to E for the outlet velocity triangle. Now let us calculate for the inlet velocity triangle. Before going to the next page and writing that, you can see that the triangle OAC and the triangle OCE are similar because the angles are similar and the height is same for both the case. So they are similar triangles. Similarly, triangle OBC and triangle OCD, the angles are same and the height is same, so they are also similar triangle. So here in this case we need U is equal to AD, which can be written as AC plus CD, but I know that triangle OBC and triangle OCD are similar, so BC will be equal to CD. So in place of CD I can write it as AC plus BC because both will be same, and AC is VU1 plus BC is VU2. So U will be equal to VU1 plus VU2. I'll write the value of U here itself. So U will be equal to VU1 is
200.
200 plus VU2 is 115.47. So U will be equal to 315.47 meter per second. Now we have these values. Now Let us find out energy transfer and see whether it's a power producing or power absorbing turbo machine. Please try to find out that and see the direction of U and VU1 and VU2. They are same here because V1 and V2 are towards right. So here energy transfer will be equal to U into VU1 minus VU2 because VU1 and VU2 are in the same direction. So if you observe, this was the direction of V1 and this was the direction of V2. So if I take the horizontal component of V1, that is VU1 will be towards right, and if I take the horizontal component of V2, that is VU2, that will also be towards right. Since they are in the same direction, we need to subtract here. So U is 315.47 multiplied by 200 minus 115.47. So we get energy transfer as what is the value of energy transfer here? It is 26.67
into 10 power 3.
Into 10 to the power of 3, I'll write it as kilo joule per kg. We have not multiplied the mass flow rate, so this will be in joule per kg. So it is 26.67 kilojoule per kg, and the sign here is positive. Since we have got a positive value, that it means to say that it's a power generating turbo machine. And if you want to find out the power developed, then you have to multiply mass flow rate to energy transfer. So I'll just write the equation here. So power developed will be equal to m dot into E or m dot into delta H naught. E and delta H naught are one and the same. So here the total change in enthalpy is 26.67 kilojoule per kg, and it's a power generating turbo machine. Now we need to find out the utilization factor. So to find out the utilization factor, if you remember the equation, utilization factor is given by, here U is same for both the case. So it is static component VR2 square minus VR1 square divided by V1 square plus, V1 square minus V2 square plus VR2 square minus VR1 square. So if you want to use this formula, then what you have to do is you need to find out VR1 as well as VR2. Or if you remember, utilization is also given by V1 square minus V2 square divided by V1 square minus R into V2 square. So if you know the degree of reaction, then you'll be able to find out energy utilization factor with the available data. We have calculated V1 and V2 already. So with that, you will be able to find out utilization factor. And if you look at the velocity triangle here, alpha 1, which is 45 degree, is equal to beta 2, and alpha 2, which is 60 degree, is equal to beta 1. If you remember the theory part, there we had discussed a special case in reaction turbine, which we called it as 50% reaction turbine. And in the case of 50% reaction turbine, alpha 1 will be equal to beta 2, and V1 will be equal to VR2, and alpha 2 will be equal to beta 1, and V2 will be equal to VR1. So if you observe the velocity triangle here, it is clear that V1 will be equal to VR2 and V2 will be equal to VR1. So this is a clear Clearly, this is a 50% reaction turbine. So now you have the required data. Either you can use R as 0.5, either you can use R as 0.5, or you can use VR1 and VR2 with V1 and V2 and calculate utilization factor. So calculate utilization factor here. Substitute V1, V2 and R will be equal to 0.5 because it's a 50% reaction turbine. So in terms of absolute values, it is 0.5. So substitute that and find out the degree of utilization factor here. So I'll substitute V1 as 282.8 squared minus V2 is 230.9 squared divided by 282.8 squared minus 0.5 into 230.9 squared. So utilization factor will be equal to ಎಷ್ಟು ಬರುತ್ತೆ ನೋಡಿ, it is 0.5.